Before we get into this one, if you enjoy these deep dives into science and reality, a quick like or subscribe goes a long way. It is a small thing on your end, but it genuinely helps this channel keep going. Now, let's begin. Tonight, we are going to answer a question that sounds simple. How big is the Andromeda Galaxy? The answer is in every astronomy textbook, every science website. It has been repeated for decades. And it is incomplete. Not incomplete in a small way, incomplete in the way that measuring the bright tip of an iceberg misses the dark mass beneath it. The tip is real, the measurement is accurate, but calling it the size of the iceberg is misleading in a way that changes everything. The Andromeda Galaxy, the closest large galaxy to us, the object that appears in every astronomy classroom and every documentary about the scale of the cosmos, is far larger than anything you have been told. And the reason most people don't know this is not because the science is recent or obscure. It is because what we call Andromeda when we show you the photograph is only the bright visible part. The rest is invisible. The rest does not show up in standard images, the rest does not get included in the number. But the rest is there. Most of what Andromeda actually is, by extent, by mass, by influence, cannot be seen with any optical telescope. And some of that invisible structure has already reached us. The Milky Way and Andromeda are not two separate galaxies waiting to collide in 4 billion years. They are two objects whose outer structures are already in contact. The merger has a date in the future. The contact already happened. Tonight, we are going to take that textbook number apart, layer by layer. We are going to look at what Andromeda actually is at each layer of its structure, how large each layer extends, what it is made of that we cannot see, what it has done to its smaller neighbours, where it is going, and what all of that means for the piece of the universe we call home. Before we start, if this kind of story is the reason you come back to science documentaries, subscribe, it helps more than you know. Now let's find out how big Andromeda really is. Start with the number, the one that gets cited in classrooms, in documentaries, in the Wikipedia article that is open in another tab somewhere. The Andromeda Galaxy is approximately 220,000 light-years across. That is already a number that defies common experience. Light travels at almost 300,000 kilometers per second. That is fast enough to circle the Earth 7 times in a single second. Fast enough to reach the Moon in 1.3 seconds. Fast enough to reach the Sun in 8 minutes. Nothing in the universe travels faster than light. It is not just that we haven't built anything fast enough, it is that the structure of space-time prevents it. Light speed is the absolute speed limit of the physical universe. At that absolute speed limit, crossing the Andromeda Galaxy from one side to the other takes 220,000 years. Our entire recorded human history, every civilization that rose and fell, every invention, every war, every written word, fits inside roughly 10,000 years. To cross Andromeda at the speed of light would take 22 of those entire recorded histories, stacked end to end. That number, 220,000 years at the speed of light, should feel enormous. It should be the headline, the thing that ends the conversation. But it is not. Because 220,000 light-years is only the beginning of what Andromeda is. This should feel enormous. It should. But here is the problem with that number. It describes the disk, the visible, bright, optically detectable disk of stars that telescopes photograph and textbooks reproduce. That disk is impressive. It contains hundreds of billions of stars. It has spiral arms, lanes of dust, regions of active star formation. But it is not the whole galaxy. When astronomers say a galaxy has a disk, they mean the part that looks like a galaxy in a photograph, the dense, luminous, photographable structure of stars and gas and dust arranged in a rotating flat plane. A galaxy's disk is what you can see in a long exposure image with a standard optical telescope. The structure has definition. It has boundaries visible against the background sky. It has spiral arms, if it is a spiral galaxy, that you can trace. The number 220,000 light-years describes that disk. The part you can see. It does not describe what surrounds the disk. It does not describe the halo. Every large galaxy, the Milky Way included, is surrounded by a vast extended structure called a stellar and gaseous halo. This halo is not a thin envelope. It is an enormous, roughly spherical region containing stars, gas, and in the case of the outer halo, hot ionized gas. The stars in the halo are older, on average, than stars in the disk. They formed in the earliest epoch of the galaxy's history and were scattered outward by the dynamics of the young, violent galaxy. The gas in the halo is a mix of material from the galaxy itself, blown out by supernova explosions, and material from the intergalactic medium being slowly pulled inward by the galaxy's gravity. The halo contains far fewer stars per unit volume than the disk. It is far dimmer. Most of it does not show up in standard telescope photographs taken with exposure times that capture the disk structure. To see the halo, you need longer exposures, more sensitive instruments, or indirect methods like the quasar absorption technique used in the 2020 Hubble study. For Andromeda, the halo is not a minor addition to the disk size. It is not a rounding correction. It dwarfs the disk. In 2020, a team of astronomers used the Hubble Space Telescope to map the extent of Andromeda's halo in unprecedented detail. The method they used is called quasar absorption spectroscopy, a technique that takes advantage of the fact that quasars are the brightest persistent objects in the universe, sitting far beyond Andromeda along the same line of sight from Earth. As the light from these distant beacons passes through Andromeda's halo on its way to us, the gas in the halo absorbs specific wavelengths of that light. The absorption signature tells astronomers that halo material is present between the quasar and the telescope. By studying dozens of quasars spread across different directions from Andromeda's center, the team could map where the halo extends and where it fades out. Some quasars showed strong halo signatures from hundreds of thousands of light-years beyond the disk. Some showed signatures more than 1 million light-years out. The map they produced was not a precise boundary. Halos do not have sharp edges, but it showed clearly how vast the structure is. What they found resized the galaxy. Andromeda's halo extends at least 1.3 million light-years from the center of the galaxy. In some directions, it may reach out to 2 million light-years. This is not an extrapolation or a model prediction. It is a measurement from absorption signatures in quasar spectra. The disk is 220,000 light-years across. The halo extends at least 1.3 million light-years from the center in some directions. At minimum, it is over 2 million light-years across, and possibly more. More than 10 times the diameter of the disk. That is Andromeda, not the 220,000 light-year disk. The full object, including the vast invisible halo, is a structure more than 2 million light-years in radius from its own center. And here is where the size question becomes something else entirely. Andromeda is 5 million light-years away from us. Andromeda's gaseous halo extends at least 1.3 million light-years from the galaxy's centre, and in some directions may reach about 2 million light-years. The Milky Way's halo extends several 100,000 light-years outward. Do the math. The halos already overlap the outermost edges of both galaxies. The extended structures that don't appear in any casual photograph have already reached each other. The merger is not a future event waiting to begin. The two galaxies are already in contact. They have been for some time. The gas from the outermost edge of Andromeda's halo is already commingling with the gas from the outermost edge of ours. This is not a theoretical prediction or a simulation result. It is a measurement. The 2020 Hubble study mapped Andromeda's halo and found it large enough to reach us. The halos are touching. The beginning of the merger, in the extended sense, is already behind us. The number in the textbook describes a disk. The galaxy is already here, and the further you look, beyond the disk, into the halo, into the dark matter envelope, the harder it becomes to say where Andromeda ends and the Milky Way begins. The boundary, at the outer edge, is not a line. It is a region of overlap where both structures are present, where gas from both galaxies has commingled, where the gravitational influence of both galaxies is being felt simultaneously. The two galaxies, in their extended forms, are already one system. The textbook number, 220,000 light-years, is the bright centre of that system. Everything surrounding it is the rest of the story. Now you know Andromeda is larger than its textbook number. But how large? And what is the halo made of? The answer to the second question is where this gets genuinely strange. The halo contains gas. Streams of warm and hot gas, some of it falling back toward the disk, some of it being pushed outward by the pressure of starlight and supernova explosions. This gas is real. It interacts with light. It was the signature the Hubble quasar study detected. But the gas is not the largest component of Andromeda's real mass. There is something else. Something that emits no light, absorbs no light, and cannot be seen by any telescope ever built. Something that has never been directly detected in any laboratory anywhere on Earth. Something that the most sensitive particle physics experiments, buried under kilometers of rock, shielded from every known particle background, have searched for across decades. Something that has not been found, but whose presence is written in the rotation curves of every large galaxy in the observable universe. Dark matter. What dark matter actually is remains one of the major open questions in physics. The particles that make it up, if it is made of particles, have not been directly detected. The leading theoretical candidate, the WIMP, was expected to show up in underground detectors and in the LHC. It has not. The parameter space of where it could hide has shrunk considerably. But it has not been found. What has been found, however, are its gravitational effects. And those effects are everywhere. A galaxy's visible stars should not be moving the way they move. If all a galaxy contained were its stars, the stars in the outer regions should be orbiting slowly, less gravity from below, slower orbital speed. Instead, they orbit at roughly constant speeds no matter how far out they sit. The gravity needed to produce that rotation pattern is far more than the stars can provide. The extra gravity comes from dark matter, an extended halo of invisible material surrounding the visible galaxy, providing the gravitational scaffolding that holds the whole structure together. For Andromeda, the dark matter halo is enormous. Estimates of its total mass suggest that dark matter makes up roughly 90% of Andromeda's total mass. The stars, gas, and dust that you can photograph, the things that make Andromeda look like a galaxy, are roughly 10% of what is actually there. Think about what that means for the size question. When you ask how big Andromeda is, and you measure the disk, you are measuring 10% of the mass of the galaxy and calling it the answer. The remaining 90%, the dark matter halo, extends even further than the gaseous halo detected by the quasar study. It is the outermost, largest, most massive component of Andromeda. And it is entirely invisible. We know it is there because of how it affects the motion of the stars we can see. A galaxy with only the mass of its visible stars would have stars in its outer regions orbiting slowly, less gravity from the center, slower circular velocity. Instead, stars in Andromeda's outer disk orbit at roughly constant speed regardless of distance from the center. The flat rotation curve is one of the clearest signatures of dark matter. Something invisible is providing the extra gravity. We can also map dark matter using gravitational lensing, the way any mass, visible or not, bends light from background objects. By measuring how much background light is bent around Andromeda, astronomers can infer the distribution of mass, including the dark matter component. We can model the dark matter halo's shape and extent using simulations that match the galaxy's observed rotation curve, the distribution of satellite galaxies, and the properties of the tidal streams from past mergers. But we cannot see it. We cannot photograph it. Every image ever taken of Andromeda shows only the visible part. The true mass of Andromeda, the dark matter halo included, is estimated at roughly 800 billion to more than 1 trillion solar masses. Some estimates place it higher. The Milky Way has a similar total mass, perhaps slightly higher in some estimates. The uncertainty is large in both cases. What is clear is that both galaxies are dominated by invisible mass. The stars and gas that make them look like galaxies are a small fraction of what is actually there, and the dark matter halos of both galaxies extend far beyond anything that shows up in any photograph. There is something worth pausing on before we continue. We have been describing Andromeda's halo as invisible, and to the naked eye and to standard telescope images, it is. But it is not undetectable. The quasar study that mapped its extent detected it indirectly. Deep ultraviolet observations have detected the hot outer halo gas directly, and some incredibly sensitive long-exposure optical images have detected the outermost stellar populations of the halo, the individual stars that inhabit the outer regions of the extended structure. In these images, Andromeda does not look like the familiar photograph. It looks like a ghost. A faint, diffuse glow extending far beyond the bright disk, covering a much larger area of the image than the part most people know. The outer regions are dim, far too dim for casual observation, but they are there, and they can be detected with dedicated observation. The true shape of Andromeda is not the disk. The disk is the bright center of a much larger, mostly invisible structure. And that structure has already reached us. Here is a clean way to picture Andromeda as it actually exists. The disk of stars 220,000 light-years across is the bright part. The glowing center. The thing in the photograph. The gaseous and stellar halo extending at least 1.3 million light-years from the center, possibly more, is the invisible fog surrounding the disk, already overlapping with ours. The dark matter halo, extending even further, perhaps several million light-years or more, is the invisible ocean in which both the fog and the disk are submerged. The true extent of the dark matter halo is not cleanly measured. It extends at least as far as the gas halo, and almost certainly further. It is where the real mass is. You are not looking at Andromeda from the outside. You are already inside some of what Andromeda is. Here is something that should be simple. Count the stars. Andromeda is the closest large galaxy to us. We have been studying it for over a century with increasingly powerful instruments. We know roughly how far away it is. We know its orientation. We have detailed maps of its disk structure. How many stars does it contain? Ask 5 different papers and you get 5 different numbers. Estimates of Andromeda's star count commonly range around 1 trillion stars, though some estimates run higher or lower. Stellar mass, the total mass locked up in those stars, is a different measurement from star count, and total mass is different again once dark matter is included. These should not be confused with each other. The uncertainty applies to all 3. That is not a small uncertainty. A trillion is 1,000 billion. The difference between a half trillion and a trillion is 500 billion stars. Why is there such large uncertainty about something we should be able to count? Several reasons. First, Andromeda is tilted. It does not face us head-on like a clock face. It is angled at roughly 77 degrees from our line of sight, nearly edge-on. This is close to the worst possible angle for counting a galaxy's stars. Looking at a spiral galaxy nearly edge-on is like trying to read the numbers on a flat disk of coins that is held up sideways in front of you. You can see the edge profile, but you cannot see how the coins are distributed across the face. Different regions overlap along the line of sight, making it impossible to say with certainty whether a given patch of light contains one dense concentration of stars or 2 sparser ones stacked behind each other. Second, dust. The disk of Andromeda, like the Milky Way's disk, contains lanes of dust along the spiral arms. This dust absorbs visible light from stars behind it. Entire regions of Andromeda's disk are partially or significantly obscured by dust that sits between us and the stars we want to count. Estimating the stellar population behind the dust requires infrared observations, which penetrate dust better, combined with models of how much dust is present and what it is absorbing. Different modelling assumptions produce different estimates. Third, the problem of resolving individual stars at 2.5 million light-years. Even with the Hubble Space Telescope, stars in Andromeda's outer disk and halo are extremely faint. In the densest inner regions of the galaxy, stars are too close together to resolve individually at this distance. They blur into a smooth glow. Counting the total stellar mass requires measuring the total brightness and making assumptions about the ratio of bright to faint stars, which varies depending on the history of star formation in that region. Each of these problems has its own uncertainty. Stack them together, and the error bar on Andromeda's total star count becomes genuinely large. Not a rounding issue, a real range of possible answers. The result is that even after decades of study, the star count for the galaxy next door has a factor of a few uncertainty. This is not a failure of science. It is an honest description of how hard measurement is at this scale. But it does matter for one reason. The star count is often used as a shorthand for size. Andromeda has 1 trillion stars, versus the Milky Way has 200 to 400 billion stars gets reported as Andromeda being larger. But if the Milky Way is more massive in dark matter terms, the comparison flips. Here is a comparison that might help anchor the uncertainty. The Milky Way is estimated to contain between 200 and 400 billion stars. That range, a factor of 2, reflects the same kinds of measurement challenges that affect the Andromeda count, applied to our own galaxy. We cannot count Milky Way stars directly either. We are inside the disk, looking outward, with dust obscuring our view in many directions. If we cannot count our own galaxy's stars precisely, it should not be surprising that Andromeda's count has uncertainty too. The difference is degree. The Milky Way is a factor of 2 uncertain. Andromeda is perhaps a factor of 3 to 5 uncertain. The challenges of measurement are similar, but Andromeda is harder because of the tilt. The simple size question leads into a question that has no clean answer. Larger by what measure? By number of visible stars, Andromeda is probably larger than the Milky Way. The most commonly cited estimates suggest Andromeda contains roughly 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. If these numbers are approximately right, Andromeda contains roughly 2 to 5 times as many stars. But by total mass including dark matter, the comparison is much closer. The Milky Way's dark matter halo may actually be more massive than Andromeda's, according to some studies. The galaxy with fewer stars might be the one with the larger gravitational influence. The comparison flips depending on what you measure. By the extent of the optical disk, Andromeda is clearly larger, 220,000 light-years across, compared to the Milky Way's estimated 100,000 to 120. 00 light-years. But this comparison is complicated by the fact that the Milky Way's disk has a broader extent in some models, and that the tilt of Andromeda makes its apparent disk size somewhat uncertain. By the extent of the halos, both are enormous. The Milky Way's halo has been estimated to extend several 100,000 light-years. Andromeda's halo extends at least 1.3 million light-years. Both halos, by any measure, are already overlapping. The bottom line is, there is no single how big answer. There is a layered answer, and each layer is a different measurement of a different component with a different level of certainty. The disk size is the most certain. The total mass is the most uncertain. The halo extent is somewhere between. What all the layers agree on is that Andromeda is much larger than the photograph suggests, that most of it is invisible, and that the boundary between Andromeda and the Milky Way, out in the extended outer structures, does not exist as a clean line. One layer of that story is written in the sky right now, if you know what to look for, the remains of what Andromeda has already done. Look at Andromeda with the right equipment and the right exposure times, and you see something that does not appear in the classic photographs. Surrounding the disk, extending tens of thousands of light-years outward in multiple directions, are faint rivers of stars. Not part of the disk's spiral arms, not part of the smooth stellar halo. Long, thin, curved streams of stars flowing in arcs around the galaxy like the wake of something that passed through. They are called tidal streams, and they are the remains of galaxies Andromeda consumed. To understand how they form, you need to understand tidal forces. When a small galaxy passes close enough to a large one, gravity does not treat all parts of it equally. The side of the small galaxy that is closer to the large galaxy is being pulled more strongly. The gravity decreases with distance, so the near side feels more pull than the far side. This difference in gravitational force across the body of the small galaxy is called a tidal force. For objects like the Moon and Earth, tidal forces produce the ocean tides, a slight stretching of the ocean toward and away from the Moon. For a small galaxy falling into the gravitational field of a large one, the tidal force is catastrophic. The small galaxy is stretched along the direction of the large galaxy's pull. Stars on the near side get pulled inward, stars on the far side get left behind. The small galaxy elongates, breaks apart, and its stars are drawn into long streams that orbit the large galaxy, gradually mixing into its stellar halo over billions of years. The process is slow by human standards. It takes hundreds of millions to billions of years for a small galaxy to be fully disrupted. But eventually the small galaxy ceases to exist as a coherent structure. Its stars, once gravitationally bound to each other, are now gravitationally bound to the object that consumed them. The most prominent of these structures around Andromeda is called the Giant Stellar Stream. It is a river of stars stretching perhaps 100,000 light-years, one of the largest substructures known around any nearby galaxy. It is the disrupted remains of a smaller galaxy that Andromeda pulled apart, stripped of its stars, and consumed. There are others. Analysis of Andromeda's halo has found multiple distinct tidal streams, each one the ghost of a former galaxy. Each one a structure that once had its own stars, its own mass, its own gravitational identity, now reduced to a faint arc of stars flowing around the thing that ate it. This is not unusual. It is how large galaxies grow. The Milky Way has done the same. The Sagittarius dwarf galaxy is currently being consumed by our galaxy. A stream of its stars already wraps around the Milky Way multiple times. But Andromeda appears to have consumed more than the Milky Way has. Its system of tidal streams is more extensive. The interpretation is that Andromeda has had a more active merger history. It encountered and absorbed more substantial galaxies in its recent past. This matters for the size question in a specific way. The mass we measure in Andromeda's disk and stellar halo today is not only the mass Andromeda formed with, it includes the mass of every galaxy it has cannibalized. The tidal streams are the accounting record of those additions. Every ghost galaxy in the halo added to Andromeda's total. The giant stellar stream alone is estimated to have come from a galaxy that may have been roughly 10 times less massive than Andromeda, something like a large dwarf galaxy or a small spiral. That mass is now part of Andromeda. Those stars, once orbiting a different center, now orbit the thing that absorbed them. Astronomers studying Andromeda's halo using the Subaru telescope, the Canada-France-Hawaii telescope, and other large instruments have mapped the stellar halo in detail and found a complex web of structures. Multiple distinct tidal streams, stellar shells, arc-like structures that form when a galaxy is absorbed nearly head-on, regions of overdensity that don't fit the smooth background halo. Each feature is a clue about a past event. Each feature adds to the picture of Andromeda as a galaxy that has been actively growing by consumption. The Milky Way has its own tidal stream debris, the Sagittarius stream, the Orphan stream, and other substructures. But Andromeda's halo appears to contain more of this material, suggesting it has had a more active recent merger history. Andromeda is larger than it started because it consumed its neighbours. It grew by pulling apart smaller galaxies and incorporating their mass, and the next object large enough to challenge that gravity is already falling toward it. That is where the story turns personal. Astronomers have known for over a century that Andromeda is approaching us. The light from Andromeda is blue-shifted toward the blue end of the spectrum, which means it is moving toward us rather than away. This makes Andromeda unusual among galaxies. The universe is expanding. The expansion of space carries most galaxies away from most other galaxies, with more distant galaxies receding faster. This is Hubble's law, the foundation of modern cosmology. The universe is getting bigger in all directions, and the galaxies embedded in it, like dots on an inflating balloon, are all moving apart. But the expansion is not the only force acting on galaxies. Gravity also acts on galaxies. When two galaxies are close enough and massive enough and have been in proximity long enough, their mutual gravity can overcome the expansion and pull them toward each other. This is what is happening between the Milky Way and Andromeda. Both galaxies, together with a collection of smaller dwarf galaxies and satellite galaxies, are gravitationally bound into a structure called the local group. The local group is not expanding, it is a closed gravitational system. Within it, the dominant members, the Milky Way and Andromeda, are falling toward each other under their combined gravity, in the same way that two massive objects thrown into space will eventually fall back together if they do not have enough velocity to escape each other's pull. Andromeda is falling toward the Milky Way, under both galaxies' combined gravity, without pause, without any force that will stop it. The only question, the one that was not answered until 2012, was exactly which direction it was coming from. What they did not know until 2012 was exactly how. Knowing something is approaching in the radial direction, directly toward you or away from you, is relatively straightforward. The Doppler shift of spectral lines gives you the approach speed, but knowing the transverse velocity, how much the object is moving sideways, is a completely different and far harder measurement. For distant objects like Andromeda, measuring transverse motion requires detecting an extremely tiny angular shift over time. The motion is real, but across the sky, Andromeda moves by an amount so small that it takes the sharpest instruments ever built to detect it. In 2012, a team of astronomers led by Roland van der Merel published the first reliable measurement of Andromeda's proper motion, its actual movement across the sky, using data from the Hubble Space Telescope. Measuring proper motion is one of the hardest things in observational astronomy. The challenge is not that Andromeda is not moving, it is moving. The challenge is that at 5 million light-years away, even a large velocity translates into an angular shift on the sky so tiny that it requires the sharpest instruments ever built, measured over a baseline of years just to detect. The van der Merel team used Hubble observations taken several years apart, comparing the position of stars in Andromeda against background quasars, which are so distant they effectively do not move on any human timescale. The shift in position between the two epochs, after careful accounting for all sources of error, revealed Andromeda's true direction of travel. The result confirmed what many had suspected but none had proven: Andromeda is moving almost directly toward us. The transverse component of its motion is small. The collision will not be a glancing blow or a near miss. It is aimed at a near head-on merger. The car is not passing on the next street. It is aimed at the intersection where you are standing. The timeline derived from these measurements places the first close approach between the two stellar disks at roughly 4 to 5 billion years from now. Within approximately 6 to 7 billion years, the two galaxies will have completed their merger and the combined object will have begun to settle into a new shape. 6 billion years sounds like a safe distance in time. But consider what that means as a fraction of the universe's age. The universe is roughly 13.8 billion years old. The merger will be complete in less than half that time from now. And consider this, the halos are already in contact. The measurement that says the star crossing is 4 billion years away is a measurement of when the dense parts arrive. The extended, diffuse, invisible parts have already reached each other. The merger, in its full sense, is already underway. The trajectory is locked. The merger is confirmed. The question is only what it will look like when it arrives, and the answer surprises most people. If you have seen a visualization of the Milky Way Andromeda merger, two spirals approaching each other, arms reaching out, eventually twisting into one, you may have felt a quiet dread. The word collision implies destruction. Two things meeting with tremendous force, and one or both of them ceasing to exist. The reality is almost the opposite. When two galaxies collide, almost nothing is destroyed. A galaxy is mostly empty space. Not empty in the sense of a vacuum chamber, but empty in the sense that the stars inside it are so far apart that the space between them dwarfs the stars themselves. The Sun is about 4 million kilometers across. The nearest star to the Sun, a small red dwarf called Proxima Centauri, is approximately 4 light-years away. That is roughly 40 trillion kilometers. Put those two numbers side by side, 1.4 million kilometers versus 40 trillion kilometers. The star is 28 million times smaller than the distance to its nearest neighbor. If you shrank the Sun to the size of a grain of sand, about 1 millimeter across, then keeping the proportions correct, the nearest neighboring grain of sand would be roughly 28 kilometers away. The two grains of sand are each about 1 millimeter. The empty space between them is 28 kilometers, and the region around them contains nothing else for kilometers in every direction. A galaxy is a collection of these grains, each separated by 28-kilometer gaps, arranged across a disk 100,000 light-years across. From a distance, all that empty space collapses into a glow. Up close, it is almost entirely nothing. When two galaxies merge, these grains of sand pass through each other's space. The probability of two stars actually colliding during a full galaxy merger is, for practical purposes, 0. The stars will rearrange. They will be thrown onto new orbits by the gravitational disturbances. Some will be flung toward the outskirts of the merged structure, some will fall inward. But the stars themselves, the grains of sand, pass through without touching. The merger is real. The collision is real. But it is a collision of emptiness, not of substance. What does not pass through cleanly is the gas. Gas clouds collide. When two galaxies merge, enormous amounts of gas slam together, compress, heat up and trigger rapid star formation. The merger of two galaxies is, paradoxically, one of the most productive events for creating new stars. Observations of merging galaxies in the distant universe, caught mid-collision by our telescopes, show intense bursts of star formation, called starbursts, driven by the gas compression of the collision. The Milky Way Andromeda merger will be spectacular in exactly this way. New stars will form in enormous numbers. When the gas clouds from both galaxies collide and compress, they trigger starbursts, explosions of star formation, far more intense than anything happening in either galaxy today. We can see this process in other galaxies. Observations of colliding galaxy pairs, captured mid-merger by telescopes, show dramatic bursts of new star formation. The Antennae galaxies, a famous pair of colliding spirals roughly 45 million light-years away, are producing new stars at a rate many times higher than either galaxy did before the collision. The interaction compressed gas, the gas-formed stars, and the resulting system is ablaze with new stellar birth. The Milky Way Andromeda collision will do the same. The starburst will increase the total light output of the combined system dramatically during the merger phase. If you were an alien astronomer billions of light-years away with a telescope pointed at the local group, you would see a brief brightening, brief on cosmic timescales, meaning tens of millions of years, as two quiet galaxies merge and ignite. From the inside, the sky will transform slowly over millions of years. The night sky, currently dominated by the band of the Milky Way, will change. Stars from Andromeda will gradually appear across the sky. The familiar Milky Way band overhead will become denser, then distorted, then accompanied by a second great arc of starlight as the galaxies approach each other. And Andromeda itself, currently a faint smudge visible only from dark locations, will grow across the sky over billions of years, becoming the most dramatic visible object in the night sky long before the first direct pass of the stellar disks. The destruction people fear is not what the merger brings. What it brings is transformation, spectacle, and eventually something completely new. But transformation is not without consequences for particular objects. Starting with ours, the Sun will survive the merger, almost certainly. What will not survive is the solar system's location within the galaxy. The gravitational chaos of two large galaxies merging reshuffles the orbits of individual stars. Stars that were in orderly circular orbits around the galactic center can be thrown onto elongated, tilted, or radically different orbits by the gravitational disturbances of the merger. Astronomers running simulations of the Milky Way Andromeda merger have tracked what happens to stars in the Sun's current region of the galaxy. The results are not gentle. Depending on the exact details of the merger dynamics, there is a meaningful probability, some simulations suggest around 50%, that the Sun ends up more than twice as far from the new galactic center as it is today. There is a smaller but real probability that it ends up much further out, or temporarily flung into the space between the galaxies during the first pass. The Sun will not be destroyed. The Earth will not be destroyed by the merger itself. The planets orbiting the Sun at distances measured in hundreds of millions of kilometers are far too tightly bound gravitationally to be stripped away by galactic-scale tidal forces. But the neighborhood changes. Think about what it means to be in a specific location inside a galaxy. The Sun currently sits roughly 26,000 light-years from the galactic center, about halfway out along one of the Milky Way's spiral arms. This position determines what the night sky looks like. It determines how bright the galaxy appears in the sky, how many stars are visible in the densest parts of the band overhead, what the background radiation environment around the solar system is. After the merger, the Sun will be somewhere else. Simulations suggest that during the first pass of the two galaxies, many stars get flung onto new orbits by the gravitational chaos. Some move inward. Some move outward. Some get temporarily ejected into the space between the merging galaxies before falling back in. The Sun has a meaningful probability, some models say near 50%, of ending up more than twice as far from the new galactic center as it currently sits. What this means for the solar system is not destruction. The Earth stays bound to the Sun by a gravitational force that requires the tidal forces of an entire galaxy to even begin to affect. They will not. The Earth-Sun bond is safe. The planets stay bound to each other. The local gravitational system we live inside is unaffected by the galactic scale shuffle. What changes is the context. The position. The view. If the Sun ends up twice as far from the new galactic center, the view from Earth will be dramatically different from what it is today. Currently, the Milky Way's galactic center, a dense, bright hub of stars, appears in the direction of Sagittarius in the night sky. It is one of the brightest regions of the galaxy visible from Earth. After the merger, if the Sun has moved much further from the new center, that central concentration will be dimmer and more distant. The new galactic center, the hub of Milkomeda, will be further away, less dominant in the sky. The night sky in 6 billion years, from a solar system that has been scattered to the outer regions of a large elliptical, will be quieter than the sky we see tonight. The the dense band of stars overhead that we call the Milky Way will be replaced by a sparser field. The galactic center will be a distant glow, not a blazing hub. But the context changes. The sky changes. The stars visible from Earth will be a completely different set. The constellations, which already drift gradually over tens of thousands of years as nearby stars move, will be unrecognizable long before the merger completes. The band of the galaxy overhead will look different. The distance to the galactic center, and thus the density of stars visible in the night sky, may be completely different. The Sun may end up in the quiet outer regions of a large elliptical galaxy, far from the dense starburst core where the merger energy concentrated. Or it may have been pulled inward, sitting in a richer, denser stellar environment. The simulations give a range of outcomes. What is fixed is this: the solar system will not be where it is now. The galaxy around it will not look like it does now, and the galaxy that emerges will look like neither parent. The Milky Way is a barred spiral galaxy, a flat disk, a central bar of stars, spiral arms sweeping outward, a dense bulge at the center. It has structure, it has pattern, it is, by galactic standards, an orderly place. You can point at a feature in the Milky Way and describe it. That region is a spiral arm. That region is the bar. That is the bulge. Structure at every scale. Andromeda is also a spiral galaxy. Its arms are slightly different from the Milky Way's, more complex, potentially distorted by its merger history, but the same fundamental type. A disk. Arms. A bulge. Two spirals, both ordered, both structured, falling toward each other at measurable speed. When two spiral galaxies merge, the product is almost always an elliptical galaxy. Most people have not looked closely at an image of an elliptical galaxy. If you have, you know immediately why they are called ellipticals. They look like nothing. A smooth, featureless oval of light, brightening toward the center, dimming toward the edge, with no feature you can point to and name. No arms, no disk, no bar, no lanes of dust, no structure whatsoever. From the outside, an elliptical galaxy looks like a galaxy that has been erased. The interesting features, the spiral arms, the disk, are gone. What remains is just the gravitational accumulation of billions of stars in a settled, featureless cloud. Ellipticals are different from spirals in almost every respect. There are no arms, no disk, no orderly rotation. Stars orbit the center in all directions, some clockwise, some counterclockwise, some in tilted paths that cut across the equatorial plane. The overall shape is a smooth, featureless oval. No structure. No pattern. Just billions of stars moving in a slowly settling gravitational cloud. If you look at images of different galaxy types, the difference is immediately obvious. A spiral galaxy looks like something. A pinwheel, a hurricane pattern, a structured disk with defined features. An elliptical galaxy looks like nothing. A smooth blob of light, gradually dimming from center to edge, with no features you could describe. The reason spirals become ellipticals is the same reason the arms exist in the first place. Spiral arms are maintained by the ordered rotation of the disk. Stars move in roughly circular orbits in the same plane and in the same direction. That order is what creates the arms, density waves moving through an ordered disk. When two spirals collide head-on, that ordered rotation is disrupted. Stars get thrown onto tilted, elongated and randomized orbits. The disk disperses. The arms unravel. What replaces them is the result of billions of stars settling under gravity into whatever orbital configuration is most stable, given all the chaos of the merger. That stable configuration, for a large merger product, is an elliptical. Ellipticals are the most common type of large galaxy in the universe. They did not form that way from the beginning. Most of them formed the same way Milky will form, through mergers. The universe is full of the products of past mergers. The Milky Way and Andromeda will add one more to the count. The combined Milky Way Andromeda system, sometimes called Milkomeda or Milkdromeda in the scientific literature, will be a large elliptical galaxy. Neither the Milky Way nor Andromeda, as structures we would recognize, will exist after the merger completes. The stars will still be there, including, almost certainly, our Sun. But they will be distributed in a new configuration, on new orbits, in a galaxy that has no spiral arms, no disk, no feature that recalls either parent. And at the center of this new elliptical galaxy, something else will be happening. Something that makes the stellar merger look like a prelude. At the center of the Milky Way sits Sagittarius A, abbreviated SCIR-A. A supermassive black hole roughly 4 million times the mass of the Sun. Its existence was confirmed through one of the most patient observational campaigns in the history of astronomy. Starting in the 1990s, two independent teams, one led by Reinhard Genzel, one by Andrea Ghez, began tracking individual stars near the center of the Milky Way using infrared telescopes that could peer through the dust obscuring the galactic center. Over decades, they watched those stars move. The orbits they traced were too fast and too tight to be explained by any mass other than a compact object of roughly 4 million solar masses sitting at the very center. One star, designated S2, was tracked through a complete orbit with a period of roughly 16 years, moving at speeds up to nearly 3% of the speed of light at closest approach. The orbit was so precise and so well measured that it became one of the most direct confirmations of a supermassive black hole in any galaxy. The 2020 Nobel Prize in Physics was awarded partly for this work. Sagittarius A is not particularly active right now. It occasionally consumes gas clouds or small objects that wander too close, producing brief flares. But for a supermassive black hole, it is quiet. Dormant, the engine at the center of the galaxy, idling, at the center of Andromeda sits a different black hole. Estimates of its mass range from roughly 100 million to 230 million solar masses. Even at the low end, it is roughly 25 times larger than Sagittarius A. By some estimates, it is the most massive object in the local group. When the galaxies merge, both black holes will end up near the center of the merged elliptical galaxy. But they will not immediately merge. Black holes do not fall through galaxies the way marbles fall through air. They interact gravitationally with the stars around them, losing energy slowly through a process called dynamical friction. The black hole pulls stars toward it as it moves, creating a slight gravitational drag that slows it down. Over millions of years, perhaps hundreds of millions, the two black holes will spiral inward toward each other. They will form a binary system, two supermassive black holes orbiting each other at enormous velocities in an incredibly tight pair, and eventually they will merge. The merger of two supermassive black holes is not a silent event. It is one of the most energetic single events possible in the universe. As the two black holes spiral together in their final orbits, they radiate gravitational waves, ripples in space-time, of extraordinary power. The gravitational wave signal from a supermassive black hole merger radiates in low-frequency bands that future gravitational wave detectors, like the proposed LISA mission, would detect from enormous distances. The event will not destroy anything around it. It will not produce a beam of high-energy radiation aimed at Earth. Black hole mergers release their energy primarily in gravitational waves, ripples in space-time itself, not in electromagnetic radiation. But the gravitational wave signal from a supermassive black hole merger of this scale will propagate outward at the speed of light, detectable in principle by any civilization in the universe with the right instruments. Future space-based gravitational wave detectors, like the proposed LISA mission, a network of spacecraft in orbit designed to detect the low-frequency gravitational waves produced by massive objects, might be capable of detecting the merger of two supermassive black holes in a galaxy billions of light-years away. The signal from two objects totaling more than 100 million solar masses would be among the strongest gravitational wave events detectable. The timeline for the black hole merger adds another layer to the story. The galaxies themselves will merge in roughly 6 to 7 billion years, but the black holes, despite being pulled toward the new center by dynamical friction, may take much longer to complete their final merger. Estimates suggest the black hole binary could exist for hundreds of millions of years or longer as the two holes slowly spiral inward through interactions with surrounding stars. So the full timeline is halo contact now, stellar disk merger in 4 to 5 billion years, full galaxy merger in 6 to 7 billion years. And then a long drawn-out spiral of two supermassive black holes over additional hundreds of millions to billions of years before the final merger radiates its energy into the universe. There is a theoretical problem with the last phase that astronomers call the final parsec problem. When two supermassive black holes are approaching each other, they initially lose energy efficiently through dynamical friction, each black hole flinging stars outward and slowing itself down in the process. But as they spiral closer, the supply of stars in the right orbits to carry energy away begins to run out. The black holes may stall at a separation of roughly 1 parsec, about 3 light years, unable to shed enough energy to spiral further inward. The resolution to this problem is not fully worked out. In a real galaxy merger, the chaotic orbital dynamics may resupply the central region with stars on the right trajectories to carry the black holes through the final parsec. Numerical simulations suggest this is likely, but the problem highlights that the final merger is not guaranteed to happen on a simple timescale. It is the last unresolved chapter of the full collision story. Whatever the timeline, the end result is the same. One black hole where two existed, one galaxy where two existed, one sky, from whatever vantage point remains, where two spirals once filled the night. The Milky Way and Andromeda will end, in a sense, twice, once when their stars and gas merge into a new shape, and once when their black holes finally combine into a single object and announce the completion to the universe in a burst of gravitational waves. The black hole merger is the final act. Everything else, the first contact of halos, the pass of the stellar disks, the starburst, the reshuffling of billions of stars into an elliptical, is the prelude. Here is something almost nobody knows. Andromeda already fills a large portion of the sky. The visible smudge, the faint patch of light visible near the constellation Andromeda on autumn nights from the northern hemisphere, is the galaxy's bright central core, the innermost concentration of stars dense enough to produce a visible glow at 2.5 million light-years. But the full extent of Andromeda on the night sky, including its full disk and inner halo, if your eyes could detect the full range of faint light, would span roughly 3 to 6 degrees across. The full moon is about 0.5 degrees across, Andromeda, in total angular extent, already covers an area of sky roughly equivalent to 30 to 100 full moons depending on which structural boundary you are using. Most of that structure is invisible to the naked eye because it is too faint. Human eyes are photon detectors optimized for a specific sensitivity range. The central core of Andromeda is bright enough to reach that threshold from a dark location. On a moonless night, away from light pollution, Andromeda's core is visible as a faint elongated smudge without any optical aid. But the outer disk and halo, which produce light far below that threshold, are invisible. To see the full extent of Andromeda, you need a camera with a long exposure time. Astrophotographers who have photographed Andromeda with hours of accumulated exposure show a completely different object from the textbook image. A vast sweeping disk that covers a significant portion of the frame, surrounded by fainter glow extending further in all directions. These photographs exist. They are available, and they show something that should permanently change how you think about that faint smudge in the sky. We have a galaxy, our nearest large neighbour, one whose halo has already reached ours, that dominates a large portion of the night sky. And it looks to the naked eye like a faint thumbprint. The universe is not hiding Andromeda. Our eyes are hiding it from us, and every second it gets slightly larger. Andromeda is approaching at roughly 110 kilometers per second along the line of sight toward us. That is about 400,000 kilometers per hour. Fast by any human standard, it would circle the Earth 10 times per second. But space is so vast that at this speed, the distance Andromeda covers in a human lifetime is negligible compared to its total distance. In 1 year, Andromeda moves approximately 3.5 billion kilometers closer. That sounds like a lot, but 3.5 billion kilometers is roughly the distance from Earth to Neptune, in a path of 2.5 million light-years. The approach is real and consistent, but on human timescales, Andromeda's position on the sky does not change detectably. Over millions of years, the change becomes visible. Over billions of years, everything changes. And that is before we account for the halo. The gaseous halo detected by the 2020 Hubble study extends to perhaps 2 million light-years from Andromeda's centre. At a distance of 2.5 million light-years, a structure 2 million light-years in radius would subtend nearly 90 degrees of arc on the night sky. It would cover almost half the sky from horizon to horizon. Andromeda's full structure covers most of the sky, we just cannot see it. And it is getting closer. Over the next billion years, Andromeda will move perceptibly closer. The angular size of its disk will increase noticeably on the cosmic timescale. The smudge you see tonight will grow, slowly at first, then faster as the distance shortens. In approximately 3.75 billion years, the first close approach of the two stellar disks will begin. The view from Earth at that point, if any observer exists, will be unlike anything in human experience. Two galactic disks, each containing hundreds of billions of stars, close enough that the stars of Andromeda resolve individually in a sky that no longer shows a single Milky Way band overhead, but two bands, weaving and braiding through each other. The starburst triggered by the gas collision will have ignited already. New stars will be forming at rates far higher than anything happening in either galaxy today. The sky will be brighter. The gas between stars will be more active. The whole visible structure of the sky will be in motion on timescales of millions of years. Then, slowly, over hundreds of millions more years, the two structures will blur into one. The arms will unravel. The disks will mix. The combined structure will settle under the pull of its own gravity into the smooth oval of a large elliptical galaxy. And the night sky, from whatever vantage point still exists inside the merged object, will go quiet. A different kind of quiet from the sky we see tonight. The quiet of a galaxy that has finished its transformation. Orderly orbits replaced by something more like a slow gravitational shuffle. No arms, no disk structure, just stars in their settled positions. Looking out into the universe from that future sky, the observer would see the same universe we see, the same cosmic web of filaments and voids, the same other galaxies at their own distances. But the Milky Way and Andromeda, the two galaxies that dominated the local group for billions of years, would both be gone. In their place, one new object, nameless unless someone is there to name it. We started with a simple question. How big is the Andromeda Galaxy exactly? And the answer turned out to have layers. The disk is 220,000 light-years across. That is the textbook number. It is real, it is accurately measured, and it describes a fraction of the real structure. The stellar halo extends further. Hundreds of thousands of light-years of stars and gas at low density surrounding the disk, contributing to the total galaxy without appearing in the standard photograph. The gaseous halo is larger still. The 2020 Hubble mapping put it at over 1.3 million light-years in radius, over 2.6 million light-years across, already overlapping with the Milky Way's outer structures, already in contact. The dark matter halo extends further than either. Invisible, dominant in mass, determining the true gravitational reach of Andromeda in a region that no light will ever illuminate for us. The star count runs from estimates of several hundred billion to over 1 trillion, with genuine uncertainty depending on how you measure, what you assume about stellar populations, and how you handle the dust that obscures large portions of the disk. The total mass, including the dark matter, is roughly comparable to the Milky Way. Neither is clearly larger in mass terms. Both are among the most massive objects for tens of millions of light-years in every direction. And all of this, the size, the mass, the layers, the reach, is moving. The whole structure is falling toward us under the pull of both galaxies' combined gravity, confirmed by precise Hubble measurement to be aimed at a near head-on collision with the galaxy we live inside. The merger will not destroy the stars. It will not destroy the solar system. The Earth will survive. But the structures we call the Milky Way and Andromeda, the spiral arms, the disks, the ordered rotation, will not survive. They will be replaced by something new. And the first phase of the transformation has already begun. The halos are in contact. The outer gaseous structure of Andromeda has already reached the outer gaseous structure of the Milky Way. The boundary between where Andromeda ends and where the Milky Way begins, out in the dark matter envelopes, in the diffuse outer halos, in the invisible extended structures, does not have a clean location. We do not live in one galaxy next to another. We do not live safely separated from Andromeda by 2.5 million light-years of empty space. We live inside the local group, a gravitationally bound system in which the Milky Way and Andromeda are the two dominant members. We live inside the early phase of a merger that started long before any human was alive to notice it, and we will not be alive to see the end. But it is ending, slowly over timescales that dwarf all of human history combined. The trajectory is locked, the collision is measured. The future is, in the broadest sense, determined. Andromeda is not a distant smudge in the sky. It is the largest structure visible from Earth, the largest thing you can see with the naked eye. A galaxy of 1 trillion stars whose outermost reach has already touched ours. It is the other half of the gravitational system we already live inside, and tonight it is 2.5 million light-years away, and getting closer every second, without pause, without hesitation, at roughly 110 kilometers per second. Good night.